Okay, so in this digital fundamentals, okay, what you will learn here is, okay, so you will learn about the binary number system, okay, which is you will learn about the science number, the flats, and etc. And in this things here also, you will learn how to convert from hexadecimal, octal, and decimal number. Okay, and then the second part here is the real numbers, which is consists of a fixed point and floating point. Okay, you will learn about these things here, and input output code, which is a BCD, ASCII, and index. Okay, so this is a table of content for digital fundamentals. Okay, so let's look at the first topics here, which is a binary number system. Okay, so digital component not only have two values. Okay, every time you learn about the digital computer, okay, there is only have two value, either that is represented by two digit, either digit 0 and 1. Okay, which is usually, okay, logic 0, sorry, voltage 0 and voltage 5 at, okay, it is denoted as a logic 0 and 1. Okay, so sometimes, okay, this binary logics can be mentioned as a on off states, ataupun sometimes we can call it as an inactive and active. Okay, which is active is for the logic 1, inactive for logic 0, not asserted and assert, and ataupun logic low and logic high. Okay, so binary logic only have two values, okay, two states, either a logic 0 and logic 1. Okay, so that is the first fundamental that you need to know. Okay, and then moving to the next slide. Okay, so this is the logic gates that you already learned in the undergrades. Okay, which is we have a lot of basics. Okay, so we have a three basic logics gates actually. Okay, which is a NOT gates, AND gates, and OR gates. And then we have another extended logic gates called a NAND gates, NOR, exclusive OR, and exclusive NOR. Okay, so this is the symbols here, and this is the function of or expression of the logics. Okay, so for example here, if you look at this NOT gate here, so the symbol here is a complement A. Okay, so this is the symbol, and this is the expression is complement A. So this is the and looking at the truth table down here. Okay, so you have an input 0 and input 1, because why it has a two input only? Because you have only one input here, so you have two combination input, either combination input of 0 or combination input of 1. Since this one here is a complement gate, so every time you put a 0 and it become, the output will be 1 lah. Okay, if you put a 1 to your input, then the output will be 0. So this is for the NOT gate. And then next, this is a AND gate. Okay, this is a symbol. So this is a standard symbol. Every time you see this symbol here, you know that this belongs to the AND gates. Okay, and this AND gate here can have at least two input or more. Okay, dia boleh ada dua input ataupun lebih. Okay, so this is the input lah. Since this is a two input, so combination of input is a 4 lah. Okay, so started with 0, 0, and it will produce 0, 0, 1, produce 0, 1, 0, produce 0. If the input is 1, 1, produce 1. So the logical end is actually is, okay, we can conclude as a, if one of the input is 0, then the output will be 0, and both input is high, and the output will be 1. Okay, then we have a NAND gate. So this NAND gate is actually a complement of AND gate. Okay, so if you see here, the output here will be complemented of this AND gate here. Okay, so when you put 0, 0, and it become 1, 0, 1, the output will be 1, 1, 0 is 1, and 1, 1 is 0. Why is it complemented? Because you see here, this at the end of this and NAND gate here, you will see the dot here. This dot here actually belong to NOT gate. Okay, actually it's something like this lah. Kalau kamu sambungkan daripada circuits, okay, it's some, sorry. You can see, all right. Actually, it's something like this lah. Okay, you have an AND gate, and then connected to NOT gate, and it become NAND gates. All right, and then we have an OR gate. So this is the symbol is A plus B. Sorry, the expression is A plus B, and this is the symbols here. So this OR gate, okay, every time the input, if one of the input is 1, then the output will be 1. Okay, and if both input are 0, then the output will be 0. So this is the truth table. 0, 0, it will produce output 0. 0, 1 is 1. 1, 0 is 1, and 1, 1 is 1. Okay, either one of the inputs getting 1s, then the output will be 1. So this is a NOR gate. NOR gate means a complement of this OR gates here. Okay, which is you put a bubble at the end of the OR gates, and the output will be complemented of this OR functions here. And then we have an exclusive OR. So this is the symbol of exclusive OR. Okay, and then this is an expression A plus. Okay, and then you have a circle inside here and B. Okay, and this is the truth table. Okay, by looking at this truth table here, you can conclude that if both input have a same input, a same value, then the output will be 0. And if the one of the input are different, then the output will be 1. So this is the output of the exclusive OR, which is if you put 0, 0, the output will be 0, 0, 1. Output will be 1, 1, 0 is 1, and 1, 1 is 0. And last but not least is a exclusive NOR lah. Okay, so this is an exclusive NOR. So you put the NOT gate at the end of the exclusive OR, and the output will be complemented. All right, and so in the numbers in the computer, okay, so the following format are often used. Okay, we have a 4 commonly formats used in the computer system, which is a decimal number. So this is what we always use in our daily life. And then we have a binary number, okay, consists of 0, 1, 0, 1, 0, 1. And then hexadecimal number, okay, which is, this is a base 16 numbers. And sometimes octal number, okay, which is a base 8 number, okay. So usually the most common number format used in computer system is decimal, binary, hexadecimal. Okay, sometimes we will look at this octal number here. Okay, so let's look at decimal number. Okay, what the decimal number looks like. Okay, so the decimal number also known as a base 10 number. Okay, dia asas 10. Okay, this number here have a 10 digits lah. Started from 0 until 9, and it will continue with a 10, 11, 12 until 19 and continues. Okay, so this is a number that we always use in our daily life. Okay, so the decimal number have a negative number as well. Okay, so the negative number are preceded with a negative sign. Okay, so this one here, this belong to negative number. Okay, so the decimal number is normally written in one of the following formats. Okay, so every time you see 56, so you know that this is a decimal number, or sometimes we write something like this, 56 base 10. Okay, so this belong to decimal number. So this is not a problem lah, because you always use in our daily life. Okay, then moving to the next slide. Okay, so this is a binary numbers. For the binary number is a means that it has a 2 state. Okay, so this binary number is a base 2 number. Okay, represent on or off state. Okay, they are either logic 0 or logic 1. So in binary number system, a digit has only 2 values, 0 and 1. Okay, starts with a 0, 1, followed by 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, and continues. Okay, so for example, okay, you have a decimal number 56, and you're going to write it in 8-bit binary. So how to write this one here? Okay, so there are 2 ways to do that. Okay, one, you can what we call here, press your calculator lah, of course. And the second one here, you can what we call here, okay, by using the weightage system. Okay, for example, okay, you have a 56, and then you're going to find out what is in binary number. So what you can do here is you you can use the weightage here. Okay, so this is 2 power of 0 is actually a 1. 2 power of 1 is 2, 4, 8, 16, 32, and then 64. Okay, since this is a 56, okay, 64 is 0 lah. Okay, and then 32, you put 132. So now 56 minus 32, then you will get 24. Okay, so you put 16, okay, minus again, and then you dapat 8 kat sini, and you put 1, okay, then you already make up a 56, and the rest you just put 0. So this is the binary representation for number 56. Okay, and the decimal number is normally written by using this format here. Okay, every time you see the 0 bit in front, okay, this 0 bit in front, you know that this belongs to binary number. Okay, and sometimes you will see this. Okay, the numbers following by this base 2, so you know that this belong to binary number. Okay, so this is the basics lah. Okay, so this is the decimal number, and this is the binary representation. Okay, so 0 is 0 lah, 1 is 1, 2 is 1 0, y is 2 is 1 0. So by using the weightage system lah. Okay, so 1 2. Okay, how to make it a 2? So you put 1 at weight 2 and 0 to weight 0 1. So you will come out with 1 0. What about 3? 3 is 2 plus 1, so you get 3. So that's why 1 1. What about 4? So 4 is 1 2 4 8. Okay, so this one here you need to put 1, and the rest you put 0 lah. So you come out with 1 0 0 4 4, and the rest is followed by using this weightage system here. Okay, so that is for the binary numbers. Okay, so let's look at the next slide. This slide here, you will learn about the common bits group in the binary numbers. Okay, so if your number of bit is 4, we can call it as a nibble. Okay, if the number bit is 8, so this is actually is a 1 byte. And if the number of bit is either a 16 or 32, we call it as a 1 word. Okay, so the word size, okay, while this one here have a 2 groups here, okay, so the word size is determined by the manufacturer. Okay, some manufacturer for Intel processors, for example, a word is represented by a 60 bit, but for ARM processor, a word is 32 bits. Okay, so this word is determined by the manufacturer. Okay, there are processors that use word size of 6, which is 2 power of n. Okay, so for the bigger sizes, double word and quad word represent 2 times or 4 times the basic word size respectively. Okay, so every time you see the 2 bytes, means that, okay, you need to multiply 8 bit by 2 lah, so you have a 16 bit. Okay, so you need to know lah these bit groups, okay, and its names here, name or labels or names here. Okay, so this is the useful reference when working with binary numbers. Okay, so usually this is okay, hold on. Okay, so this the number of bits is represented by n, and now we're going to find out what is the largest value. Okay, so the largest value represented by the n bits is you can calculate it by 2n minus 2 power of n minus 1. Okay, for example, if the number of bit is 1, okay, so the largest value is 1 lah. If you have the numbers of bit is 2, okay, so then I just simply write here. Okay, the number of bit is 2, then the largest number value here can be represented by 2 bits is 3, okay, which is 2 power of minus 1 equal to 2 power of 1, which is All right. Then you can started with uh 000110 and 11. Okay, so this 11 here is represented by 3. Okay, and it will keep increase depending on these numbers lah. Okay, if 3, so if 3 is started with 000 until 111. So this is the number of bits. Okay, so started with decimal 0 until decimal 7. So the maximum value here is 7. Okay, and then this is a prefix for a lot of data. Okay, so this is what we always use in our daily life here. Okay, kilo represented by 2 power of 10, mega represented by 2 power of 20, gigabyte, giga 2 power 30. But okay, so sorry. So this is what we use in our daily life. Okay, which is kilo 10 power of 3, but in the binary it represents by 2 power of 10. Okay, for mega, okay, we usually use a 10 power of 6. Okay, but in power of 2, okay, in the binary number there is a 2 power of 20 for mega. Giga is 2 power of 30, but in the what we call here a decimal number is actually as 10 power of 9. Okay, so you need to remember all these things here. Okay, next is hexadecimal numbers. Okay, so the hexadecimal numbers mean 16. Okay, so it is actually a base 16 number and popularly called a hex number. Okay, sometimes every time you will see the hex means that it is a hexadecimal number. So in the hex system, a digit can take the value from 0 to 9 and then followed by A through F. Okay, so 0 is actually represented by 0 in decimal. 1, 2, 3, 4, 5, 6 until 9 also similar to the decimal. But to represent number 10, okay, in hexadecimal it is labeled as a A, 11 is B, 12 C, and if F it is actually a 15. Okay, so this hexadecimal number is used as a shortcut in writing a binary number, because if you write in a binary number, so it's too long. So to make it shortcut, you can use the hexadecimal number. Okay, so it is written in the following formats. Okay, so every time you see this dollar signs, or sometimes you see the 0x or H at the back. Okay, so all of these are belong to hexadecimal number. Okay, next, this slide here, this is for the signs number. Okay, so negative number are represented in a 2 complements. Okay, so every time you have a 2 complements, you know that that is a negative number. But of course lah, it is depend on the most significant bit. Either your sign, the most significant bit, or sometimes we call it a sign bit. Either is show labeled as 0 or 1. If 0, then you know that it's a positive number. If 1, you know it is belong to negative number. So this is what we call it as a MSB, which is a sign bit. Yeah. Okay, so example here. Okay, so let's look at this example. Okay, -5. Okay, so how to represent -5 in binary? Okay, to represent a -5 in 8-bit binary, so what you're going to do here is first, okay, we need to find out what is the 5 in the binary number. Okay, so started with 1, 2, 4, 8, 16, 32, 64, 1 to 8. This is an 8-bit number. So to represent number 5, what you're going to do here is, okay, you need to find the binary number first, which is 4 plus 1 is 5, and the rest you just put 0, 0, 0, 0, 0, 0. But this is a positive 5. Okay, this number here represents positive 5. Okay, now you're going to make it as a negative 5. So how to do it? To do it, okay, you need to do the second complement. Okay, so change this one here to second complement. Okay, there are 2 methods to do that. Okay. Okay, one of the method here is, what you need to do here is, okay, the first method, okay, to do a second complement, okay, first you convert this number, okay, this positive number using a first complement, okay, which is you complement this number here, and then after that you add with 1. Okay, that is the first method. Okay, the second method here is, okay, this is the shortcut method lah. Okay, which is you traverse bit from right to left. Okay, kamu cari daripada kanan ke kiri. Okay, and then find the first bit. Okay, since this is the first bit, what you need to do here is you just copy this bit here. Okay, ambil semula bit ni, copy back. And what about the rest? The rest you just complement. Okay, so this is become 1, 0, 1, 1, 1, 1, and 1. So now this number here is actually represented by negative 5. Okay, so this is how to convert lah from decimal, negative decimal, and to represent in binary number. First, you need to find out what is the binary representation for positive 5. After that, you do the second complement and you will get the negative value. Okay, and if you have this value here and you're going to find out what are the, what we call here, what is the number. Okay, so macam mana nak buat? Okay, first, okay, always this is a MSB. Okay, so let's say lah kalau kamu ada macam ni lah, right, 1 1 1 1 1 0 1 1, and you're going to figure out, okay, what this binary number represent for. Okay, berapakah dia punya decimal number. Okay, since if this number here is a sign number, so what you're going to do here is, first, okay, you locate this sign bit, which is your MSB. Okay, since this MSB here showing a 1, okay, so you know that, okay, since the sign is 1, so you know that this is a belong to negative number. So what you're going to do after you identify this is a negative number, so by using a second complement, okay, you change to find the magnitude. Okay, so sama juga lah, we use the second method, which is traverse from right to left, find the first number 1. So this is the first number 1, you copy back, and the rest you just complement. Okay, and then you will get this value here. Okay, since this value here is, okay, 0 0 0 0 1 0 1, and then now by using the weightage system, you find out what is the number. So this is a number 5. Okay, after you multiply all the weight here, okay, you find out this represent number 5. And since this one here is a negative, so you just put negative 5. So the answer is negative 5. So this is only valid for signed number lah. Okay, for example here, we have this unsigned number. Okay, the same value. Okay, the same number here, but it is an unsigned number. So what you're going to do? Because this is an unsigned number, so you just simply put the calculate, multiply the weightage, and you will obtain the 2 5 1. Okay, the same value, but if it is a signed number, it will represent a negative 5. If unsigned number, it will represent a 2 5 1. Okay, so this is the how to do a two complements lah. Okay, as I mentioned earlier, we have method 1 and method 2. Okay, so this is a method 1. Okay, so this is a given number. So what you're going to do here is you find the first complement, and then after that you add with 1. Or this is a quick method here, which is you traverse from right to the left, find the first bit, okay, for the first 1 bit, and then copy this bit here, and the rest you just complement. Okay, for example, this one here. Kalau kamu tengok this one, okay, daripada kanan ke kiri, so this is the first bit. Okay, so everything from here you need to copy back. Okay, so this is you copy back, and the rest nanti you complement. So that's why you get this value. Okay, any question up until here? Okay, if no question, then we go to the sign extension. Okay, so this sign extension is a must when you're moving a second complement data to a bigger register. Okay, because sometimes your register is 8-bit. Okay, and some of the register is maybe a 16-bit register. So what you're going to do, if you have an 8-bit number and then you're going to copy this number here to 16-bit register. So what you're going to do here is you simply copy the sign bit to fill the new high order bits. Okay, for examples. Okay, hundreds in 8 bits. Okay, if this is positive hundreds, okay, so let's this is a sign number lah. Okay, since it is positive 100, so this is the value of the positive 100 of 8 bits. Okay, if you want to copy this number here to 60 bits, so what happened here is, okay, the computer will copy this sign number and extend it to this bit here. Okay, so it becomes 000011001000. Okay, if you have the negative hundreds, okay, so what you're going to do, okay, so this is a negative 100 representation, okay, and then the computer, the CPU, will take this sign bit and extend it to this bit here to make a 16-bit number. So the 16-bit for negative 100 is represented by 11111110011110. So now the sign bit, okay, belong to this bit here, which is this your MSB, which is it is actually a sign bit. Yes, so this is for sign extension. Okay, now we go to the real numbers. Okay, so the real number can be represented by the whole number and fraction number. Okay, nombor bulat dan nombor perpuluhan. Okay, so the fraction, okay, consists of, for example, 0.25, and then you have a pi, okay, 3.142, and require a special consideration. Okay, there are 3 different representation most popular, but to represent the fraction number. Okay, first we call it as a number system, which is a fixed point fx. Okay, so this is sufficient for simple application. And then we have a floating point. Okay, so wide number range, complex hardware, and rational, which is less common compared to fx and fp. So the number system that always used to represent the real number is some called a fixed point or floating point. Okay, so the fixed point is on the floating point will consist of nombor bulat, okay, the whole number as well as the fraction number. Okay, so let's look at the Q format. Okay, so Q format is a number format for fixed point number. Okay, which is it written as a QM.N or QN. Okay, so what this M and N represent for? Okay, so M is actually the number of integer bit. Okay, and N is a number of fractional bit. Right? So the total number of bit in a data word sama dengan, okay, equal to sign bit plus M plus N. Okay, so this is the example of possible 8-bit cube format number. Okay, we have a total of 4 cube format number. Okay, for Q70, okay, what this Q70 represent? Okay, so kalau kamu tengok kat sini, okay, so this 7 here is actually, okay, Q70. So this is your M and this is your N. Okay, means that, so this is actually, you have a 7, what we call here, numbers of an integer, but 0 fractional bit, 0 fractional number, tak ada nombor perpuluhan. Okay, so this is the binary sequence. Okay, 0, Okay, so this green color here stand for sign bit. Kalau kosong is a positive number. If 1, it is belong to negative number. And the blue here is actually the magnitude, okay, the number of integer bits. Since this doesn't have any fractional number, so that's why the decimal range is from -1 to 8 to 1 to 7. Okay, then if you use the Q6.1 format, okay, you know that this one here, you have 6 magnitude or 6 number of integer bits and 1 fractional bit. Okay, satu nombor perpuluhan. So this is the nombor perpuluhan, represent the number perpuluhan, and this is of course lah the sign bit, and this is the magnitude. Okay, the number of integer bit. Okay, so the decimal range is started from -64 to +65. 63.5. Okay, and then if you have use the Q3.4 format, okay, so in this format here, okay, 3 number of integer bits. Okay, you have 3 number of integer bits. Okay, if you 3 means that is start the maximum is 111 lah. Okay, and then all right, so this one is your fractional number. So you have a 4, 4 perpuluhan. And if you use the Q07 or sometimes it's Q7, okay, means that this one, all of the 7 bits are represented by fractional numbers. Okay, so this is the range from -1 until plus 0.992187. Okay, so store and so this Q format is stored and manipulated as a regular binary sign integer by standard integer hardware. Okay, there are 2 conflict notation here. Okay, to need to be considered. Okay, sign bit is not counted as an integer. Okay, so this sign bit here kita tak kira sebagai integer. Okay, and the sign bit is counted as integer if we use this format here. Okay, Q80. So the sign bit is what we call counted as integer. If the sign bit is not counted as integer, we use the Q7, this format here, Q7.0. But commonly we use this notation compared to this notation. Okay, so to avoid confusion, the total number of bits must be specified. Okay, choosing the position of the binary point depends on the largest number needed for the given algorithm and the tolerable error either is required a precision. Okay, so this is more details on the how to what we call here, how to read this Q format here. Okay, so let's look at the Q34. Okay, since this is a Q34, so you know that 3 here is belong to number of integer, and 4 here belong to the fractional number, nombor perpuluhan. Okay, so first, okay, so this is your sign bits. Okay, the green color here, followed by 3 bits for integer. Okay, because you have a 3 bits for integer and 4 bit for fractional part. Okay, so this sign bits, okay, you can represent something like this lah. Okay, if you're going to find out what is the value here, okay, you can put the weightage something like this. Okay, for the sign bit, this is actually a -2 power of 3. Why is this one is -2 power of 3? Because you have the binary point here. Okay, so this is a binary point. So now you're going to put the weightage. So this one here is a 2 power of 0, and this is 2 power of 1, 2 power of 2, and this is supposed to be the 2 power of 3. But since this is a sign bits, you can need to put 2 power of -3. Okay, what about the fractional part? The fractional part is this one is 2 power of -1. Okay, so this is 2 power of -2, 2 power of -3, and this is a 2 power of -4. Okay, sorry. This one not 2 power of minus 3. Negative 2 power of 3. Okay, sorry. For this part, negative 2 power of 3. Okay. So this is the weightage. Negative 8, 4, 2, 1. And 2 power of minus 1 is actually 1 over 2 equal to 0.5. Okay, for this one here, this is 1 over 2 power of 2, which is 1 over 4, equivalent to 0.25. And the rest is going to follow lah, right? So let's look at the examples here. Okay, you are given this value 0, 1, 0, 1. Okay, and then dot 1, 1, 0, 0. Okay, so this number is represented by Q34 format. Okay, so now you're going to find out what is the value in decimal number. Okay, so what are you going to do? Okay, first, okay, we locate the binary point. So this is the binary point. Then you calculate the weightage lah. Okay, so this is 1, 2, 4. And since this is a sign number, okay, this is represent the sign number. So this is negative 2 power of 3, which is negative 8. Okay, and what about this one here? This is a 1 over 2. This is 1 over 4, 1 over 8, and this is 1 over 60. Okay, and then you multiply the weightage and you add them together. Okay, so this is 4 plus with 1, and then plus with 0.5, and plus with 0.25, and then you will get 5.75 base 10. Okay, so this is the jawaban. Okay, for the Q7, okay, sama juga. Okay, so let's look at the Q7 format. Okay, so the Q7 is actually 0 integer bits, while you have 7 fractional bit. Okay, for example, you have this value here, 0, 1, 1, 1, 1, 1, 1, 1. So what are you going to do? Okay, so you locate the binary point. So this is a binary point. Okay, and since this one here is a sign number, okay, so you calculate the voltage, the what we call here, the weightage, which this is actually 2 power of 0, but since it's a sign number, so you can need to put a negative lah, negative 2 power of 0. And what about the rest? Okay, so this one is 2 power of negative 1, 2 power of negative 2, 2 power of negative 3, and it's continued. Okay, and then after that you multiply the weightage, or to make it more simple, okay, after you do something like this, okay, so what you can do here is to make it more simple. Okay, so this one here is actually 2 power of 6 plus 2 power of 5 plus 2 power of 4 plus 2 power of 3, 2 power of 2 plus 2 power of 1 plus 2 power of 2 divided with 2 power of 7. Okay, and then you will get something like this after you calculate, and this is the fractional number that you will get. Okay, you can change this one here from here become this. Okay, so for the Q7 multiplication, if you multiply Q7 with Q7, okay, if the number of bit is 8 bit, multiply with 8 bit, you will get a 16 bit number. Okay, so now what you're going to do here is, okay, after you multiply this 8 bit by 8 bit, okay, next to stay in a Q7 system, okay, you need to maintain 8 most useful bit, which is the 8 most useful bit is this bit here, okay, which is started with bit 14 until bit 7 only. Okay, so this is the most useful bit for the Q7 system. Okay, for example here, okay, you're going to multiply 0.5 multiply with 0.75. Okay, the answer will be 0.375, or in the binary, you're going to multiply 0.1, okay, base 2 multiply with 0.11. Okay, this is the value, and this value here is around this value lah, which is 0.011, and the rest is 0. Okay, so you need to keep this tempat, this location only, okay, for this Q7 multiplication. Okay, so this is a floating point. So the floating point represents the fractional number with a greater range. Okay, so floating point computation is handled by the FPU, which is a floating point unit on the CPU if available, or by a software routine. So numbers are represented by us based on the scientific notation. Okay, so most of the floating point format of IEEE 754 are either a single precision 32-bit or double precision 64-bit. Okay, if you're going to represent the number with a greater range, with the greater what you call fractional numbers, so we can use the floating point numbers. Okay, which is this floating point number have either have a two type, single precision, which is up to 32-bit precision, and double precision up to 64-bit. Okay, so let's do the IEEE single precision format, which is consists of 32-bit. Okay, so this is the number of bit started with a 0 to 31 bit. Okay, so bit 31 is actually your sign bit. Okay, this is a sign bits. So this is your most significant bit. Most significant bit is for the sign bit. Okay, if this bit here is 0, so it represents a positive number. If bit here is 1, it will represent a negative number. Okay, and then followed by 8 bit for exponent. Okay, so this is an unsigned 8 bit. Okay, which is biased at -1 to 7, and the rest is 23 bit for mantissa. Okay, so for example here, okay, so this IEEE in the single precision format range from this number here, okay, plus minus 1.175 darab 10 -38, okay, and until this number here. Okay, so this is for the single precision, which is consists of 32-bit, while double precision, okay, consists of 64-bit. Okay, again, the most significant bit, which is bit 63, is for the sign bits, and it has a 11-bit for exponent and 52-bit for mantissa. Okay, so this is a exponent lah. 11-bit exponent, which is up to 1023. Tadi, kalau kamu tengok tadi, 8-bit, which is exponent up to -127. Alright, so this is the magnitude, okay, for the single precision and double precision. Okay, and this is a variation of IEEE 754 format, okay, which is you have the half. Half is 2 byte, okay. For the 2 byte, you have a 1 sign bit, 5 exponent, and 10 significant bit. Okay, kalau 2 byte here, okay, you know that 2 byte is actually a 16-bit lah. Okay, so that's why 10 tambah 5 tambah 1, and it total is 16-bit. Okay, if B float, okay, so this was also a 2 byte. Okay, which is 1 byte is for the sign bit, 8 bit for the exponent, and another 7 bit is for significant bits. Alright, single 4 byte. Okay, kalau 4 byte is 32 bit, which is the single precision, double precision, double extended, and quad. Okay, but the things that we always use here is somewhere these two here. Okay, single precision and double precision format. Okay, so this is a single precision versus double precision. Okay, so actually, okay, for the single precision, is used where the precision matter less. Contohnya simple program like games. Okay, if you using a games, okay, you're going to write a game, you can use a single precision. And for the double precision, use where precision matter more. Okay, if you're going to if the precision is matters, so you use the double precision. And this double precision always used in a complex program like a scientific calculator. Okay, so this is the example lah. If you try this code here, okay, so what happened here? Okay, this code will give the different fractional number lah. Okay, different nombor perpuluhan. Okay, so this is for the double precision, which is up to this number here. And for the single precision, only up to this number here. Okay, so 0.33334. But this one here will give more precision lah in terms of the nombor perpuluhan. Okay, and then this is the what we call here the table, okay, or the summaries of the single precision and double precision. So in the single precision, 32 bits are used to represent the floating point number. Okay, 8 bits for exponent, and in single precision, 22 bits are used for mantissa. Okay, so single precision 32 bits, double precision using a 64 bit, while 8 bits used for the exponent. For double precision, 11 bit for exponent. Okay, so this is up to -127, and this is -1023. And for the mantissa, okay, 23 for the mantissa and 52 bit for the mantissa for double precision. And this is the bias lah yang saya kata tadi. Okay, so this is 127 bias for, kenapa 127? Because it is a bit for exponent. So the bias is 127 lah, the maximum. For the this one here, okay, the bias is 1023. Okay, because it is 11 bit. Okay, the range number from this number here, and this is the range number for the double precision. Okay, so this is used where the precision matter less lah. Okay, kalau you're going to write a program with a less precision matters, so you can opt for using a single precision. Okay, and it is used for wide representation. Okay, and this is called a binary 32. Okay, while for the double precision, used where the precision matter more, and it is used to minimization of approximation. Okay, so to minimize approximation, okay, so you can use the double precision. So this is the approximation lah. Okay, and then so this one here always used in a complex program. Okay, so this is another example. Okay, to verify in a single precision. Okay, you can run this program here. Okay, dekat sini nanti. Okay, you just click this one here, copy this program and see the output. Okay, so this is in what we call here. Okay, so this is in hexa lah. Hexadecimal. And this is the decimal representation. Okay, so actually, if you convert this value here, you will get this value in decimal number. Okay, so this is for double precision. Okay, so you run this program here. So this is the value lah in hexa that you will get. Okay, kalau kamu, if you count this one here, okay, so this is 64 bit lah. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it has a 8 byte, so it is a 64 bit. While this one kalau kamu kira 1, 2, 3, 4 darab 8 is 32 bit. Okay, and this is a 64 bit. And this is represented by what we call here hexadecimal, and this is actually in the decimal number, right? So this, okay, and now moving to this slide here. So this is the fixed point versus the floating point. Okay, since both fixed point and floating point can use to represent a fractional number, but now we're going to see what are different between these two format. Okay, for fixed point arithmetic, so it's a less accurate lah compared to floating point arithmetics. Okay, so floating point number, the fractional number is more accurate compared to the fixed point. Okay, and it has a small range of value. Okay, only up to, kalau kamu tengok yang Q.7 tadi, only up to 7 tepat perpuluhan, but this one here have wider range of values. Okay, so fixed point always use in a built-in circuit. Okay, so this one here, you can use it in a built-in circuit for software implementation or hardware floating point unit on the higher cost device. Okay, and usually this fixed point format used when the cost of power is more important, and this one here for the floating point arithmetic used when the accuracy is more important. Okay, so this is the table of comparison lah between the fixed point or floating point whenever you're going to decide to use, every time you're going to use the fractional number or nombor per puluhan. Any question up until here? Ada soalan tak? If no soalan, I think we take a 10 minutes break, and then after that we continue back. Boleh ya? Okay, for the input output code, we have a few input or output codes that we always use. Okay, one of them is called as a binary code decimal. Okay, a BCD. Okay, so what this BCD do? Okay, so the BCD is used for the 7-segment display. Okay, which is this 7-segment display is, you can find it everywhere. Okay, you can find it on your previously lah. Okay, before we have a smartwatch. Okay, you can find it in your watch. Okay, your digital watch, or you can find it in a billboard. Okay, by some of them using a 7-segment display, before they're using LEDs. All right, and then okay, and then in the old car, okay, you can find the 7-segment display to display the temperature, either high or low, or on the clock or inside the car as well, using the 7-segment display. Okay, so this actually, okay, the computer don't use the BCD internally, so the conversion to the BCD is done in output routine. Okay, actually this binary code decimal is used to display the numbers or sometimes the alphabetical in the 7-segment. Okay, so this is the standard lah. Okay, the standard binary code decimal, which is for the binary code decimal, it use the 84 8421 method, okay, to display the this number on the BCDs lah. Okay, for example, you're going to display number 7. So what happened here? To display a number 7, okay, the code to display number 7 is, okay, by using the 8421 method, okay, you know that 4 plus 2 plus 1, which is equal to 7. So this is the code lah, okay, the code used to display number 7. Okay, so this code here, when you put this code here to number 7, and the decoder will decode lah, okay, what are the LEDs to drive in the 7 segment. Okay, by right, the LED is something like this. For the 7 segment display, you have a total of 8 LEDs. Okay, so this is denoted as A, B, C, D, E, F, G, and this decimal point here is H. Okay, so this LED will be light up according to the code that you will what we call here insert, okay, that you will put to this decoder. Okay, for example, if you're going to display number 7, so you need to put 0111 to this decoder, and then this decoder will drive only LED A, B, and C turn on, while the rest will be turned off, and then you will so the number 7 will be displayed on the 7 segment. Okay, of course lah, if you learn in as you learn in the what we call undergraduates, okay, this 7 segment display have 2 types. Okay, one is a common ended, and then the other one is common gated. Okay, for example here, okay, you're going to display a number 2. Okay, you 2 on your 7 segment. So what are the codes? What is the code that you need to put to your decoder? Okay, since it is the number 2 by using the 8421 method, so you know that to display number 2, you just put 1 to your 2, and the rest you put 0. So this is the value. And for number 3, which is, okay, the code that you need to put here is 0011. So the number that will drive to your 7 segment is 3. Okay, if you have the sequence of the binary numbers, something like this, so before it goes to the 7 segment display, what happened here is this number here, okay, will be divided into 4-bit group lah, because we use the BCD. BCD is a 4-bit group of the number, so it will be divided into this thing here. Okay, 1, 2, 3, 4, 1, 2, 3, is it? Okay, so this one not lah, okay, because this one is different from this number here. Okay, so actually it will be something like this lah. You give the value, okay, and then this value here will be divided into 4-bit groups, and then that groups will it will decode it to this number here will be go to your decoder and will display the numbers. Okay, that is for the BCD. And then we have the ASCII. Okay, so this is a American Standard Code for information interchange defined as a binary pattern for letters A. Okay, if you're going to write a email, write a program, write letters, okay, we're using the ASCII code. Okay, so it is actually a combination of letter A to Z, capital A to Z, and smaller a to Z, symbols, number from 0 to 9, and device control codes. Okay, so what you see on your keyboard is actually using the ASCII code. Okay, so only 7 bits are defined by the standard, but normally appended with a 0, making it 8 bits. Okay, so usually the ASCII code have 7 bits ASCII code numbers. Okay, the ASCII represent letter from American English. Okay, so if you use the standard what we call here ASCII code, you can only use the standard letter for American English. Okay, if you're going to use the other language such as Japanese, okay, Japanese character, Chinese character, and then Arabic character, so you need to use another code called Unicode. Okay, so Unicode is a very established to display other than American English letters. Okay. In fact, if you're going to use the yen symbol, the euro symbol, the pound sterling symbol, you cannot use using the ASCII code. You need to use the Unicode. Okay, so this is the ASCII code chart. Okay, so this is represented by the hexadecimal number, and this is a hexadecimal number. Okay, so this is the what we call here a standard function in ASCII, and this is the symbol that available in the ASCII, and this is the numbers, and this is the letters. Okay, for example here, if you're going to use a delete del here, okay, so what number that you need to use? Okay, the number here will be 07FF. Okay, so this is depending on this value je lah. Okay, every time you put a value and then it will translate to this okay, whatever value that you put, and it will translate to this table here. Contoh lah kalau kamu masukkan, okay, you're going to display R, okay, to your monitor. So the R will represent by this value 05 and then 02. So this in hexadecimal, 0502 will represent the capital R. Okay, if you're going to use the zero value here, so the value that the unit the computer will reach is 04F. Okay, something like that. Okay, sorry, not 052. Salah ya. 52 because it only consists of 7 bits. Okay, so this is a 4F. Okay, sorry, my mistake, because ASCII is 7 bit. Okay, so this is 4 bit, and yang ni lagi another 4 bit. Okay, actually this is a 3 bit lah kat sini, but dia up to 7 only, from 000 until 111, and this one here is 0000 until 111. Okay, then we have the parity. Okay, so this parity is a simple form for error correction. Okay, so every time you're going to check for errors, so if you can use the parity codes. Okay, so a big string has a odd even parity on the number of 1 in the starting, in the string is odd even. So this is the what we call decimal value, and this is the binary value, and it will consist of the parity number. Okay, hold on. I need to take a phone call. Sekejap . Okay, so this is an even parity example for the ASCII. Okay, if you're going to show the S, okay, so the ASCII code for the S, and this is with the even parity. Okay, so you put, okay, the value is 0 kat situ. So this ASCII code is used to transfer or store parity ASCII data is in the bytes 1 byte. Okay, so this is 1 byte lah. Kenapa 1 byte? Because it consists of 8 bit number. So this parity bit is removed before it is used. Okay, sebelum this one here go to the decoder, okay, it will be removed first, and then after that it will translate to based on these tables kat sini. Okay, so contoh kat sini, if you see here, this is capital S. Capital S is 0110101. Okay, if you look at this table here, okay, where is the capital S? Okay, so this is the capital S. Okay, so the value here is 101. This is for 5 lah. Okay, 101, and followed by 3. 3 is 0011. Okay, and last but not least, okay, the Indianness. Okay, so this one is, yeah, okay, you kena tahulah how the Indianness works. So the Indian is the order of how a sequence of byte or word is stored in a memory. Okay, so if you're using a big Indian, okay, there are three types of Indians: big Indian, little Indian, or byte Indian. Okay, but most of the computer use either big Indian and little Indian lah. Okay, so the big Indian store the most significant byte of a word at the smallest memory address. Okay, so you put the most significant bit first, followed by the less significant bit to your memory. Okay, while the little Indian store the least significant byte at the smaller address first and followed by the rest. Okay, contoh. Okay, so contoh lah, this is a contoh. Okay, you have a 32-bit register and this is the data inside the registers. Okay, so this is the register, 32-bit register, and this is your memory. Okay, your memory size is only 8-bit. Okay, the memory is 8-bit. So what happened here is from this 32-bit register, the value inside this 32-bit register, you need to chunk it to 8-bit by 8-bit. Okay, kamu kena kecilkan dia sebagai 8-bit by 8-bit. So kita potong dulu. Okay, make it 8-bit by 8-bit because the size of memory is 8-bit. By using a big Indian, okay, so the memory, usually the memory on top of this memory here is a smallest memory lah, and this is the highest memory value. Okay, so what happened here is for the big Indian, we take the most significant byte to this here, means that we store the most significant bit byte and then followed by the second most. Okay, and this one, and lastly is the least significant byte is stored, okay, at this location here. Okay, meanwhile for the little Indian, again this memory is a 8-bit, but your register is 32-bit. So what happened here is sama juga, we divide it into 8-bit chunks. Okay, we kecilkan this to 8-bit chunks, and then for this one here, the low significant byte is stored first, kita, okay, and followed by other bytes, and the most significant byte is stored last. Okay, so and the byte Indian, okay, means that some CPU support switchable Indianness for both BE or LE. Okay, sometimes you can use a big Indian or if you and then you can switch it to the little Indian, okay, by using the programming lah, okay, to switch either to use a little or big Indian. Okay, so that's it for the module 0, which is to the overview of the fundamental of digital. Okay, any question up until here?